Hello.
Hello,
How
we're
are
back
you?
again.
What's going on?
Yeah, all good over here. Yourself?
Pretty good, no complaints.
Nice.
We had a little bit of trouble last time trying to make this video because there was a storm coming through here.
Yes, absolutely. It wrecked with the audio, wrecked with the visual. It almost kicked
Everything,
me out at one
everything.
point.
Did they give that storm a name?
They did, but what it was, I don't remember.
Did they?
So,
Well, so okay,
never
so
mind.
it was serious. Well, we made it through. We made it through. All right. Well, I think we're going to be talking about Fisher's exact test.
Yes,
Exact.
it is pretty exact, as was Fisher. He was considered to be the father of modern statistics, and that is what we remember him for.
Wonderful. Well, that's good. I should have known that, I guess. I mean, I know the name. I've heard the name over and over and over again, of course, but didn't realize. Well, thank goodness. We appreciate all the effort and all the knowledge, right?
Indeed,
Well,
yes.
so you're gonna explain it to me now, right?
I'll give it a best shot. It is a non-parametric test of associativity, so it's on the same par as the Spearman's and the Kendall tests.
Okay.
And
All right. Okay. And
we
it's
have,
got factorials back there, I see.
it
So
does,
A plus B, C plus D collectively factorials, A, C,
yep,
A. Okay.
there's meant to be a factorial over there as well.
Oh, is there? Okay. All
It's
right.
been
Fair
cut
enough.
off.
Fair enough. Fair enough. We could, the audience could fill in the blanks, as they move along. So it's not just, us presenting something. They go beyond and they explore and find out what's on what's beyond the boundaries. Right?
Love that.
So, so it looks probably like a contingency table, right? Is it a,
Yes,
a test for independence?
it is, yes, and it's similar to the chi-squared test, but very slightly different how it works. Because a chi-squared test is used to test associativity between, well, both of them associativity between categorical variables, but the chi-squared uses the test statistic and the sampling distribution to calculate the p-value. But with small sample sizes, that just gets really weird. It
Yeah.
breaks down, doesn't work. So what Fisher's exact test does, it calculates all possible contingency tables and compares them with the observed value that you have.
Okay.
It calculates the p-value
All
from the
right.
proportion of all possible tables which are more extreme than the one that you have.
Okay. All right. All right.
Mhm.
So for smaller sample sizes, basically.
It is, yeah.
Okay. Well, that's
It
very, very useful because a lot of the assumptions, of course, that we're making when we're doing these tests, you can't meet with small sample sizes. All
indeed,
right.
yes.
Okay. So let's see here. If you give me 2 seconds,
Sure.
I'm gonna open up a an Excel sheet, a fresh Excel sheet. I'm gonna open up.
Love that.
You do
No
you?
blue
Okay.
Peter over here.
Hold on. Hold on. Let me get a nice fresh one here. Uh, where is it? God, I've got a lot of stuff over here.
Oh no.
Okay, here I got one right now. Let me share it. Oh, sometimes, sometimes I can navigate through these windows easily,
That's
sometimes
okay.
not so easily. Okay, let me see here if I can share this bit now.
Well, while you grab that,
Okay,
I'll talk a little bit more about the sample size if you like.
please do, please do.
So Fisher's exact test will work for any sample size, but it's used mainly for small. Firstly, because chi-squared doesn't work with small sample sizes, but also because Fisher's exact test becomes incredibly unwieldy with larger sample sizes, and it just gets a bit too much of a hassle. Can't be bothered to do all that. Let's work with what we have. Chi-squared for large, Fisher's exact for small. Hey, there we go.
Oh, here it is. Okay. Oh man, where is it? Is this the one? It's like small over here. Here we go. Oh, I could expand it. I think I'm expanding it. Hold on.
Oh, love it.
No, something happened there. Close that. Oh my. Oh Lordy, Lordy, Lord. Oh, let me see if I can move this thing. Come on.
Please stand by for technical difficulties.
Oh my God, I can't believe I can't move this thing. Hold on. Let's try this. Not that. You guys, you see something right now?
We can, yes, you did Blue Peter it.
Wait a minute. Is this it right here? Is this me? No?
What do you mean, sorry? We've got the Excel sheet open and I can see class 1, class 2 with red and blue.
You can see what? Say again. I'm sorry.
I can see the Excel sheet with class 1 and class 2 and red and blue.
Aha. So you caught me in a lie, didn't you? Because I
Maybe.
said that I was opening a fresh one, huh? Oh my Lord. Hold on. How's our audience gonna believe me from now on?
Oh no. Do you want to stop this video and start again?
No, 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 I don't think so. I don't think so.
We employ statistical honesty over
Or we
here.
can decide later. Oh my God. We're showing out. Let's see. Let's see. All right. How about this one? Man, I thought I'd get away with that. Oh, here it is. Back again. Okay.
Back again.
All right. Forgive me. Forgive me. All right. So we went through a little bit of an example here.
Mm-hmm.
And we laid out a contingency table. So that's kind of what I have here, right?
Mm-hmm.
Okay. And we have two different categories here, blue and red. We have two different categories here, class 1, class 2. So we're basically trying to see if it's a test for independence, is whether our odds change of being in class 1, given that we're in given that we're blue or red.
Right.
Right? Okay, so if the probability changes of being in class 1, if I'm in red, right? If given that I'm in red, that means that those two events would be dependent. Okay. So the equation that you were showing earlier, that's in the, well, actually now that we're seeing,
Mm-hmm.
right? We've got A, B, C, and D, right? And what we've done is we've shown all the different combinations that we can get. Okay, so very generally speaking, what we may have in this contingency table, but we do have an example over here with actual numbers in it, specific numbers. Okay.
Nice.
All right. So the equation turned out to be, what was it? I'm going to put it in here if I may.
Oh, okay. So we're
Okay.
calculating the p-value.
Okay, so right here, I'm gonna reproduce this like we did before, right?
Nice.
Did I? Okay.
Okay.
So, like I tried to hide to pretend that I didn't do. Okay, so let's call it again p-value. All right, okay.
Okay.
And I believe what we had was, I'm gonna write it up here because
Sure.
I'm not sure. Just so we can have it here in front of us. So just as a text, parenthesis A plus B,
Yep.
close that. That's factorial,
That's
right?
factorial. Yep.
Then we have, go ahead, read it out to me.
C plus D
C plus D.
factorial.
Close that.
So these
Factorial,
are the rows in
right?
the contingency table, and then we've got to do
Okay.
columns. So A plus C factorial,
A plus C factorial.
and then multiplied by B plus D factorial, and the factorial is missing is over there. Just like how the P is missing over there.
What's missing? I'm sorry.
Sorry, don't worry, talking to us.
Oh,
D
I
plus
the audience. Okay,
sorry,
D plus
B plus D.
D plus D. Thanks. You stop talking to me. Oh my God, I'm floundering. All right, here we go. So that's in the numerator.
Mm-hmm.
Oops.
Oh,
No,
we need a
oh,
factorial.
there is.
There we go, that's it.
Okay. Now that's gonna be all over.
Mm-hmm.
Should I put it down here?
You can do.
All right, let's do that. All
So
over.
gonna need A factorial.
Oh, just A by itself. A
It is A by
factorial?
itself, yep. Then b factorial.
All right, b factorial. Let me guess what's next. C factorial,
Yep.
d factorial.
And then last one.
Oh, there it is. Okay. And oh no, not capital N. N factorial. Okay, so that's all right. So just to make sure, should we put a little division line in here? Oh, so ready? What? Cancel. Oops, I don't
Oh,
want to do that.
yes, of
Okay,
that.
there we go. Okay, so imagine there's a division line right here, everybody.
Yes.
Okay, so let's go on and see if we can calculate exactly the same bit here
Oh, it's going to take
as we
ages in
did
Excel, isn't it?
before. Oh my God. Okay. All right. As soon as I make a false move, yell out, okay?
Right.
So equals open paren. Oh, no, 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 fact, right? FAC, fact. A plus B. Bam,
Yep.
this guy plus this guy, right?
Nice.
All right, so close that times. All right, yeah, open
Yes.
parenthesis. Oh, no, fact again.
No.
God,
Yep.
I forget that at some point. Fact, and that's C and D.
It
So
is.
this guy plus this, close, parenthesis, times.
Now you got to do the columns.
Fact, now on a roll here.
Nice.
Which way? Five of these guys right here?
That's right. Yep.
A and C, right? A and C, A plus C. Beautiful. Close that. Plus
Oh, times.
times. Sorry. Fact. Uh, uh, that's the last one up top, right? I
It
hope.
is the last one.
Ah, this is exhausting. Five. This five plus the one right under it, 65.
Nice.
Close that. Now divided by, and then I'm going to open a parenthesis for the whole
That'd be
denominator.
wise.
Okay.
Yep.
So now we need fact. A.
Hmm.
Boom. That's that guy. Close that. Be nice if they just used exclamation mark here instead of fact.
Right.
I'm asking for too much, yeah.
This is the downside of using a spreadsheet tool rather than a software.
Yeah, you're right. You're right. Absolutely, man. Should we ditch it and go to R? No, I'm kidding.
No, we're almost done.
No, we're all the way. We're almost done. Fact B, right?
You got B, yes.
That's
So
this.
that
Oops, no,
is
this B.
K7, yeah.
That's the B. Okay, not the letter B. Yes, comma, not comma, times.
Times.
Fact again. Oh, it's almost there. C, that's this
Hmm.
guy. Yeah, yeah,
Yep.
that's that guy. Times fact of this guy, D, yeah.
Mhm.
Close that, and now times fact of the total amount, N, right here,
Yes.
right? Close, and then close parenthesis for the division. Cross our
Yep.
fingers. All right.
It
Love it,
worked.
man. We came out, it worked again. Okay, so we could put in, and in fact, I imagine if we go in here and change these to bigger numbers or to smaller numbers, but in the same proportions, I should mention this. I've run this test before, and I'm using the chi-square distribution,
Right.
and it comes out as not an we can't reject the null hypothesis of independence. So we can't really prove that it's a the two events are dependent on each other.
Okay.
But it comes kind of close, it gives us a p-value that's just above the 5. So it looks pretty consistent. I'm wondering now if we change these values with the same proportions, across A, B, C, and D, but maybe make those numbers smaller. Like maybe divide each one of them by 5.
Sure.
We'll
Okay.
try that and we'll see what happens to these bits right here.
Well,
Okay.
let me write that p-value down, and then we got it. 0.0996337. Right, we'll compare.
Mhm.
If we change the numbers but keep the proportions, we will see if that p-value changes.
Yeah. So I'm just basically, I can divide each one of these by 5, it looks like, right?
Yeah?
That's really a small sample. All right, so that's going to be a 1. That'll be a 5. This will be a 1. And this will be a 13, right?
Yep.
13. Yeah, significantly changes, doesn't it?
Well, that's way different.
Yeah, yeah. I mean, they're both insignificant, right?
Mm,
I mean, if we take, I mean, it does make sense that we'd be getting bigger p-values for smaller values there.
mm.
But I mean, in both cases, they turn out to be insignificant.
Yeah.
These, I'm going to multiply each of these by 10, just out of curiosity. But that is giving us more information too, meaning that even in a chi-square test, still should get, how do you call it? In a chi-square test, you might get a bigger chance of finding something significant if there's more information.
Right.
So, yeah, I'm gonna just try that. Is that okay?
Yeah, let's
All
go for
right.
it.
So I'm gonna change this to 10. 10, this to 50. This to 10 again. And now who's gonna tell us what 13 times 5? So, oh, 130, right? No, not 130. Yeah, 130,
Yeah,
right?
yeah, 130.
What am I talking
I thought you
about?
were
I
kidding
can
then,
multiply
sorry.
by 10. Oh, what happened? Not even a number? Oops.
Okay.
What happened here? What happened here? What does it say?
Oh, what does it say? Number error.
Number error. Really?
Bizarre.
180, 200? What is going on? Why? It was 1? Yeah. That's weird, eh? Let's go back to this. 5, 5. Nope, 5, sorry, 5. Was it
That was
25?
25, and the other
25.
was
That was
65, I believe.
65. And this was 5, right? Yeah.
Yeah,
Okay. That's weird, eh?
that is weird.
That's weird. I wonder. Oh, I know why.
Why?
Because we're trying to figure out factorials of stuff, numbers like more than 100, 200 factorial. That's probably
Oh,
like a really,
yeah.
really big number. So I think that's where that error is coming in. Okay. All right. I think that's it.
We said at the beginning that Fisher's exact test works with small sample sizes because bigger
Okay. All
sample.
right. There's the proof.
Did not put two and two together.
Oh my God. That was like almost gave me a heart attack. All
I was like,
right.
what? Why?
Wow, that was cool, man. That was cool. So,
That's great.
all right. Pretty cool. That was fun actually, because especially with the trying to get that lie across, but we'll see. We might keep it just to show that at least everybody out there, Laura was not in on it, man. I was all on me. So I'll take the sin. All right, Laura, it's always a pleasure.
Indeed. Well,
I'll see you in
we
the next one,
shall.
okay?
Sorry, say again?
I said I'll see you in the next one. If you
Oh, yeah,
decide,
of
if you
course.
decide you want to make another one.
Oh, well, let's see if I can handle the deception the second time.
Okay.
There we
Okay.
go. Right.
All right. I'll
We'll say
talk to you
bye.
soon. Bye-bye.